All right, guys, these are some practice-free response problems. Now, if you'll notice before you did this, some of you I accidentally told you to pull up the other version, and the other version is this. However, what we have done is I told you last year was the first year that the test was redesigned for new curriculum and new things. And what they did is they took all those old questions and things that are not really going to be tested upon anymore, or they were a little over the top for this particular chapter. They've pulled them out, and so they've reduced them down to these. I think it's just one short quick little page that's got this many questions on it. So we can actually go through it relatively quickly, and it's all based on stoichiometry. So let's look at a few of these questions. All right, answer the following question about this thing. Now, I want to talk about what this thing is because some of you may not know what it is. First of all, what is beryllium? What is Be? Beryllium. What is C2O4? That's oxalate, okay? That's one you may not have heard of or seen very often. That is beryllium oxalate. And then it says talk about beryllium oxalate and its hydrate. As soon as you see hydrate, what does that mean in terms of the compound itself on a molecular level? It's got waters attached to it, okay? Now, we also can call that a dot water. Calculate the mass percent of carbon in the hydrated form of a solid that has the formula beryllium oxalate, and then how do we name this? Trihydrate. Remember, the number of waters just turns into a prefix, and you call the water a hydrate. So beryllium oxalate trihydrate is how we're going to name that. Now let's talk about this for just a second. Mass percent. What do we know the basic definition of percent stands for? Part over whole. Very good. So specifically, they're asking for the mass percent, right? So we're wanting to know part of mass and the whole mass. What part are they specifically asking you to find? Carbon. So they're wanting to know how much carbon is in that whole entire thing, right? So, again, if you want to go all the way to the bottom of this and like add a page and you can start writing, that will be fine. Or if you want to write on your own paper or whatever, it's up to you guys. Okay? So, specifically, how much carbon, it's, let me change this. So BeC2O4.3H2O. All right, so how much of that mass can you recognize as carbon before you ever begin? How much mass? What? Very good, 24.02. How did you know 24.02 grams of carbon? Very good. Carbon is 12.01, and how many carbons do you have? 2 of them. All right, now, how would you figure out the whole? Figure out every bit of it, right? So, see if you guys can do that real quick. Maybe you can do it faster than I can. Now, what's the easy part about the mass? What can you do with this 3 in that water? Very good. Multiply that times 18.02. 3 times 18.02. All right, it's going to give me a number. Plus 16 times 4. Plus 24. Oh, do you have to include 24.02 in your total calculation? Yes, because it's also a part of it. And then beryllium is 9.01. If I do a 9, not a 3. And so that's going to give me a total mass of 51.09 grams. Okay. Then what do you do? Divide. I had the key somewhere, and I have found it. There we go. Okay. Now, not only do you have to divide, what else do you have to do? Very good. All percents must be multiplied by 100. And hopefully the answer you came out with real quick, it doesn't say in the question, but I'm just going to go ahead and round it to 3 significant figures. Is that, excuse me? Is it dead? Yeah. If it's dead, put it up on top of that second file cabinet on your right. Thank you. Okay. Is that the percentage you guys got? No? Yeah. Allison, what's wrong? Honestly, was that a difficult question? No. It really wasn't. The key to all of this was recognizing two things. Number one, you need to know what mass percent is. Mass percent is simply part divided by whole. The second thing is you need to know how to get a total mass of this thing. Honestly, on the AP exam or on a test, if you solve this thing, would that thing freak you out? Yeah. I mean, those hydrates are pretty scary formulas if you've never seen them, and that's why I wanted to show it to you. Okay? All right. Let's move on to the second part. B. When heated to 220 degrees Celsius, beryllium oxalate trihydrate dehydrates completely. All right, so let's talk about what that means. What does it mean to dehydrate completely? Every bit of that water is gone. So all molecules of water have been flushed out of the entire molecule. All right, and do you agree that this would be the reaction? The hard part for students to recognize is this thing right here. They want to think that these two things are both reactants when in essence it's one whole compound, right? It's one thing you can pour into your hand, and it splits into these two things. Here's something important to note. What did it turn into? Okay, it left that solid and it turned the liquid into a gas. Clay, you good? Okay, all right. So this is the reaction. If 3.21 grams of the hydrate is heated to that temperature, calculate the mass of beryllium oxalate solid that is formed. What have they just asked you to do? It's going from what to what? Yes, ma'am.
Is Hannah pondering class?
Yes, ma'am.
She is?
Yeah. So in basic essence, they gave you grams of one compound, right? They gave you grams of this, and what do they ask you to do? Convert it to grams of something else. Is that just not a gram-to-gram conversion?
But wouldn't we have to first figure out, because it's beryllium oxalate with the water.
Uh-huh.
So we'd have to find out how much of that 3.21 grams is beryllium oxalate, and then find the mass of it.
It's so basically, I gave you 3.21 grams of this whole thing. Okay, I poured that in your hand, 3.21 grams of this whole entire compound. Okay, and I want to know how many grams that is of that. So it's essentially, I'm saying if I give you grams of X, and I want to know how many grams of Y it is. It's just a regular 3-step. The thing that looks weird is because that big old hydrate's plugged in. Okay, all right, so let's do that. So we're going to do 3.21 grams, and I'm just going to write hydrate because I don't feel like writing that whole thing out. Okay, we've already solved for the mass of that thing, hadn't we? What was it? 151.09 grams are in 1 mole. By the way, real quick, let's go back and look for just a second. Let me clear this. Is that whole entire equation balanced as is? Yeah, it's balanced. So what's your mole to mole ratio? Again, where you're going to see that is going to be right here and right here. It's 1 to 1. Very good. All right. So we know that it's going to be a 1 mole of BeC2O4 to 1 mole of the hydrate. And then I need 1 mole of beryllium oxalate into grams of the same thing. Figuring out the mass of beryllium oxalate should be really easy. How could you do it real simply? Okay, why? Go ahead, Clay. Okay, but remember, you're looking at the hydrate in terms of the water. This whole entire thing is one compound. It's one compound. Okay, so the coefficient goes out in front of it. Again, this is not a. That's why I said at the very beginning. A lot of students misuse this. It's because they're wanting to use this. Let me change colors. They're wanting to use this dot like a plus, and it's not. It's one entity. It's one compound. Okay, so the coefficients come from here and they come from here, which is a 1 to 1. Now, if you were trying to find out how much water was produced, yeah, it would be a 1-to-3 ratio with water, but it's a 1-to-1 with beryllium oxalate. Okay. All right, Parker, you said to easily find the mass of beryllium oxalate. What you said, subtract what? From what? Okay. Why are you subtracting 54 from 151? The hydrate had what? 3 waters. And what's the only difference between the hydrate and the solid? The 3 waters. So 3 times 18 is about 54.03 or 06, my bad. So going back to this one, do you already have it? What is it? 97.03? 97.03. Or you could do it the old-fashioned way and just do it how you always do it. Just trying to give you a different way to think about it. So if I know there's 3 waters, each water is 18. 3 times 18 is 54. Just subtract it from the other thing. Okay. All right. Run that math real quick, guys. How many significant figures should your answer have? 3. Very good. Cannon, you got it? Nope. Seth, you got it? Okay. $2.06. Is that days to the weekend? Grams of beryllium oxalate. So, all that was a gram-to-gram conversion. Real simple. 2.06 grams of beryllium oxalate. Oxalate. Sorry, I was thinking acetate and oxalate. No. I was thinking acetate, and I was like, that's not right. But here's the thing that I want to point out. So far, has this been a pretty simple problem? And notice, this was the year 2000 exam. This was on the test in 2000. I mean, I'd be okay with having this question on the exam. It's not too terribly difficult. All right. Now, let's do double I. This was going to change some things up. The volume of water released. They just flipped something on us. They want to know the volume of water released when you're measured at that temperature and that pressure. All right, so I'm actually going to let you guys think about this one for just a second. See if you can figure out what you need to do. See if you can figure out what you need to do. I hope some of you come up with it. Hopefully, you all at least did this. That everybody at least get it to water, because you know you're going to need water. Now, I stopped at moles for a specific reason. Anybody get the correct number of moles here? What was the number of moles of water? .0637 moles of water. All right. Now, I know what you're thinking. Why in the world did you just stop at moles? Because what are they asking for? The volume. I have moles. They want volume. But what other pieces of data did they give me in the question specifically? Look at that. They gave me some temperature and they gave me a pressure. So let's think. I have moles. They've given me pressure. They've given me temperature. And I need volume. Hopefully you know to use what? Pivnert. Did anybody get that far? Right. You knew to use it, didn't know what to do. All right. So again, this is why this is a training exercise. I'm trying to teach you how to logically think through these things. So we need PV equals nRT. Algebraically, what do we need? How can we arrange? What are we rearranging this for? Volume. So what is volume going to equal? Very good. Now, we know one of our values. We know moles because we just solved for it. 0.0637 moles. All right. R. This is the important one. Hush for just a second because some of you may not know this. But first of all, I've told you we have two R's. We have an energy R and a gas R. Which R would this be? Why gas? Because we would need gases. What's the numerical value of the gas R? 0. Hush, Parker. I know you know it. I know you know it. I'm asking other people. But I didn't teach everybody last year. 0.0821 unit. I'm asking anybody. Latum over molk. It's important that you understand that. Temperature. The temperature that they gave us on the thing was what? Okay, numerical value. Okay, it was 220 Celsius. However, according to our R unit, what must it be in? Kelvin. Okay, 220 plus, how do I get it to Kelvin? At 273. Okay, so 220 plus 273, so we're looking at 493. 493 Kelvin, all divided by the pressure that they gave us. This is, wait a second, let's go back and look at this for just a second. Notice this one. This is a new one for a lot of you. This is the one that's going to challenge you guys. I'm going to be honest, this one's happens very rarely. Okay, this is a new teaching topic. It happens very rarely, but it will pop up later on in the year. According to our R unit, what must our pressure be in? All right, according to R, we need it in atmospheres. However, they gave it to us in millimeters of mercury. So I'm just going to write it up here. So they gave us, what was it, 735? All right, so 735 millimeters of mercury. Here's what I want you to do. It's just like a stoichiometric conversion. Millimeters of mercury, we can go into atmospheres. Someone besides you, do you know, does anybody remember this conversion? I'm proud that you remember it, but I'm asking other people. What is the conversion of atmospheres to millimeters of mercury? What? Very good. Remember, millimeters of mercury. What is millimeters measuring? Millimeters measures what? Millimeters. Distance. You okay. All right. The way we got millimeters of mercury from atmospheres. Atmospheres is the pressure that's pushing down on us right now. In a barometer, the pressure at 1 atm moves mercury 760 millimeters in a tube. Okay, just to kind of draw you this picture, let's pretend that we have a petri dish, and in this petri dish there's kind of like this tube coming up, and this thing is filled with mercury. Okay, when we have 1 atmosphere of pressure pushing down on this tube, what's going to happen is mercury is going to go up into this tube exactly 760 millimeters. Does that make sense? Okay, that's where that number comes from. All right, so in this, it's going to be 760 millimeters of mercury in 1 atm. So, 735. Oh, my calculator just went off. Someone's got to help me out. 97? 0.967 atms. All right, so let's look at our units. Will moles cancel? Yep. Will atmospheres cancel? What else cancels? Leaving you with? What were you asking to find? Is liters okay? Okay, try to find that answer. So, now that you've seen it, does it make a little bit more sense? This is the step that probably would have gotten most of you at this point in the stage of your academic career in this class. By the end of this class, the day you take the exam, you're going to look at this and you're going to laugh and you're going to know exactly what to do because you're going to have practiced this so often. You're going to know you're going to have to go from grams to moles because as soon as you have a temperature and a pressure and some type of gram or moles, you will always know to go straight into this. There's an additional topic that I want to bring up about this particular question. And I'm going to go back and I'm going to change it right here. And this is what I want you to add, or somehow in this particular question. Basically, so part B. Part B. This is something that some of you may not know yet. I need you to grasp this concept. Instead, what if it said the volume of water released if it was measured at STP? This is something that's new that I haven't covered a whole lot. What does STP stand for? Right, very good. So STP stands for standard temperature and pressure. Standard temperature and pressure. Miss Hicks talked about this last year? She may have hit it, but not quite. Okay. All right. Now, there are values that go with this. Here's the most important thing for you to remember. At STP, we have the standard temperature is 0 degrees Celsius, which is 273 Kelvin. 1 ATM, 1 mole, and 22.4 liters. The biggest thing that you need to get out of this is this right here. At STP, 1 mole is equal to 22.4 liters. At STP, 1 mole is equal to 22.4 liters. And I can prove to you mathematically where this came from. I can prove it mathematically. I'm not going to do the actual numbers, but I'm going to show you. If we did PivNerd again, and I wrote it V equals nRT over P. Here's mathematically how this will work. If I plug in 1 for N, why is 1 going in for N? What is N? 1 mole. R is the gas law, right? 0.0821. T would be what? 273, all divided by what value? 1. So what are the only two numbers you're really multiplying together? Do that for me just to prove it to yourself. Do 0.0821 times 273 and tell me what you get. 0.0821, don't say it out loud, just look. 0.0821 times 273. What'd you get, Avery? 22.41. That's where it comes from. So it's not just some number we pull randomly out of the air. It's mathematically based around the ideal gas law. So that's where that number comes from. So if part B was like this, and it says calculate the volume released at STP, the first thing you should have done, do you agree, would be to at least find the number of moles. Okay? Then what could you have done and not had to have used PivNerd? Instead of having to plug in 1 ATM and 273 here, you could have done it in a stoichiometric relationship. Let me show you what you could have done. You could have said 0.06, was it 37? Moles of H2O. And in 1 mole, how many liters? And you're done. That's all you would have to do. That's how they want you to do it. What's wrong with that? It is easy. But it's wonderfully easy. But when is this only true? Only at STP. That's the only time you can use that relationship. That's it. It makes it a lot easier. A lot easier. Remember, 22.4 is a reduced version of that right there. Remember that's why I proved it to you mathematically. You can plug it into Pivnerd, but
You could only do that if you were looking for volume
at STP. That's it. Okay, at STP. Because 1 mole is equal to that many liters. But are we working with 1 mole? We're a little less. But when you do the math, it will give you the number of liters. Okay, again, only at STP. Any questions? Okay. All right, so here's what I want to do. I'm actually going to shift gears, and I'm going to go into the multiple choice part of it real quick. All right, so let me pause the video. Number 1 does not make any sense at all. I even looked at their key, and their key makes no sense. Like, it does not make sense whatsoever. So we're going to omit number 1. I think what happened is they changed the question, and they messed it up somehow, and even their answer key is way off. Yes, sir. I do have another one. If you'll come up here, you can have it. Does anybody else need one? Come on. Okay, take that in, please. Now, number 2 is a good one, and I like it because it's forcing you into remembering something. It's forcing you into that atom. You need another one? Okay. That atom to molecule ratio. 22 grams of this compound will contain that many atoms of what? Oxygen. All right. So what you're going to have to do is take one of these compounds and convert it into that many atoms of oxygen. Okay? So I'm just going to pick a random one to start with. Let's just pick C to begin with, or carbon dioxide. So in 22 grams of CO2 times, what's the mass of carbon dioxide? 44.01. All right. You should. I promise eventually you'll get those down. And in 1 mole of CO2, this is when that mole-to-mole relationship of atom to molecule comes into place. In 1 CO2, how many O's are there? 2 O's. So 2 moles of oxygen. But here's the deal. Can I stop right there? What was the question asking you for specifically? Atoms. So, in 1 mole of O, whenever you see atoms, what's the answer always going to be? Say that again? I'd rather hear Avogadro's number, which is 6.02 times 10 to what? 23rd. I really, really, really hope you do not have to put this in a calculator. Please don't look at it in terms of its math. I want you to look at it in terms of its relationship. Think for just a second. What is 22 divided by 44? Huh? It's 0.5. It's half. You're right. I was looking at you like, yes, you're right. Okay. What is 2 divided by 0.5? 1. What is 1 times Avogadro's number? Avogadro's number. What were they asking you for?
A way to pick a random one.
Do you see what I just did there, though? Sometimes you don't need a calculator to do this. Sometimes you don't need a calculator to do this. So here's what would have happened. We got the right answer because I just got lucky and picked the right one the first time. What if you would have done this, though? What if you would have picked water? Do you agree it would be 18 over 1? And then in 1 water, there's 1 oxygen. And then it would be Avogadro's number again? If you look at that one, hopefully you should recognize that 22 divided by 18, when you multiply that times Avogadro's number, is that going to give you Avogadro's number again? No. You could do it for any of them. Sometimes you don't even have to plug it in the calculator. I want you guys to get used to looking at numbers as numbers and not try to plug them in as numbers in the calculator. Look at relationships. Look at ratios. You know that 22 divided by 44 is half. Half divided by 2 is 1. And then 1 times Avogadro's number is Avogadro's number. It's a training method. Okay? Looking at 3, I would hope that none of you would have to even do the math on number 3. Look at 3. The question is, the substance that contains the highest percentage of oxygen. Well, let's think. What does percentage mean? Part over whole. Well, let's think about this for just a second. What part would oxygen be if there was only one oxygen? Huh? If there was one oxygen, it would be how many? 16. All right, so we know that there's at least 16 grams in that. There's at least 16 grams in that. There's at least 32 grams. 16 times 4 is what, 96? All right, and then 11 times 16. That's a good one.
16 times 4 is 64.
Oh, my bad. Not 96, 64. Sorry. All right, 176. All right, so do you agree that you have the amount of oxygen in each one of these compounds present? Which one of these is the closest to its whole? Which one of those is closest to its whole? D. Obviously. Yes. 176 to 342. 64 to 136. That one, and that one. Obviously, to me, 16 is closest to 18. So, without even having to do any math, have I been able to determine what my answer is? Absolutely. What if the question was the opposite? Pick the substance with the least percentage. Which one would that be? Well, when you go, let's see, 176 divided by 342, and then 64 divided by 136. This one actually comes out to be 51%, and this one is actually 47%. So it would be what? B. Here's what would happen on the day of the exam. You would plug every single one of those numbers into the calculator, wouldn't you? You would. You would plug every single one of them in there. Here's what, if you had no clue what to do, here's what a lot of people will do. A lot of people, let me clear this, will pick this one. Why do you think they'll pick that one? Because it has the highest number of oxygens. You would be shocked at how many people that were like, I have no clue, and pick A because it has the most number of oxygens. Be honest. You know that people will do that. It's going to happen. That's why I'm trying to teach you to find these little things. Percentage, part over whole. You know how to do that. Okay, so don't let that confuse you. Don't let that make you freak you out. Okay? All right, 4. The mass of that many atoms of hydrogen gas is equal to. Do we even really need to do this? But I guarantee you some of you would miss it. And here's why. Why is it a little more difficult than it looks? What is hydrogen gas? A lot of you would do it as 1H. So when you go from atoms, remember if you're going from one compound to the same, can't you go from atoms to grams? You can skip the mole step, right? So when you do Avogadro's number times the grams, it's 2.02. So you would pull this number down. You'd pull that number down, and it's 6.02 times 10 to the 23rd. But the point that I would try to make is that people would miss that because what would they put when it says hydrogen gas? They're going to put 1.01. They do that for a reason. Okay? All right, guys. Y'all have a good day.